This presentation is talking about the paper with the title of Visual Positioning System for Indoor Blind Navigation. The traditional travel aids for the visually impaired people are white cane and guide dog. Although the white cane provides obstacle detection and below the vest protection, it is ineffective in detecting overhang obstacles and it lacks wayfinding function. On the other hand, guide dog is superior to the white cane in many aspects, but there is the cost of training as well as the care and feeding of the animal over its service time. To mitigate the issues, researchers have developed many robotic navigational aids to assist the blind folks for wayfinding and obstacle avoidance. Among these devices, we focus on the vision-based systems. Navigational aids have been proposed for obstacle avoidance by building a local 3D map from the camera's data. Robot Vision Kit implements RGB SLAM for pose estimation and 3D mapping. The output dense 3D map is used to detect obstacles and the traversable floor area. Kinect can attaches a Kinect sensor on a white can and scan the environments to detect the obstacle's boundaries. RealSense Glass is a wearable navigational device. It installs a RealSense RGB camera on a 3D printed frame. It detects the floor plan as the traversable area. Those devices lack the global localization function for wayfinding. Some other systems use global information, that is, some pre-installed global map to localize the user for wayfinding. ICRA uses video features, whereas Navicock utilizes the Bluetooth energy to localize the blind traveler in some particular environment. However, they both require burdensome pre-engineering work. ICRA needs to extract a great number of video features to create ADF map, while Navicock needs to deploy the Bluetooth beacons that cannot be easily deployed in general indoor scenarios. Therefore, to address these issues, we propose a new robotic navigation aid called Robocane. The key distinct feature of Robocane is that it effectively bridges the local and global navigation functions on a portable device. For the local level, we propose a depth-enhanced visual inertial odometry for pose estimation, and we utilize the traversability field histogram method to detect obstacles. For the global level, we implement a floor plan-based particle filter approach to localize the user's position in the environment. It does not require pre-engineering work, but only a prior floor plan map, which is accessible for almost every building. The device is portable and user-friendly. The RGB camera we use is RealSense D435. The MU is VN100. The software is implemented on the upboard computer. It is a credit card-sized board with various I/O interfaces and GPIO pins. The active rolling tip consists of a rolling tip, a DC motor, a motor driver, and an electromagnetic clutch. The upboard controls the clutch and the motor driver to steering the RNA to point to a desired travel direction. The pipeline of the Robocane software system is shown here. The data acquisition sends cameras and IMU's data to DVIO for real-time pose estimation. The terrain mapping creates a 2D world grid map, which is used for obstacle avoidance and particle filter localization. Based on the Robocane's location in the floor plan, the path planning module determines the heading direction towards the next point of interest. This information is passed to the obstacle avoidance module to compute the desired travel direction without colliding with the surrounding obstacles. The active rolling tip steers the Robocane into the desired travel direction, and the speech interface sends audio navigation commands to the blind traveler via the Bluetooth headset. The modules in the pipeline can be roughly divided into local and global parts, as highlighted here. The figures below briefly show their results. On the right, the local modules estimate pose, generates a 3D map, detects obstacles, whereas on the left, the global parts localize the user's position in the 2D floor plan, generates a path and guides the user to move towards the destination. Together, the Robocane can effectively guide the user for obstacle avoidance and wayfinding. DVIO was developed based on Wins model. It increases pose estimation accuracy by using depth data in 2 ways. First, it classifies the video features into near-range and far-range categories. For the near-range features, their depth measurements are very accurate, so the inverse depths of these features are kept constant in the optimization process. For the far-range features, their depths are assigned as unknown, and we use epipolar geometry constraint to model these far-range features measurements. On the other hand, DVIO extracts the floor plan from the depth data and uses it as a geometric feature to constrain the pose estimation. According to Hartley and Zitterman's book, the transfer error only considers the error on one image, and a better model is Sampson error that measures the error on both images. An example is showing here. A feature points observation on image I and j are xi and xj. Xj prime is the xi's reprojected point on image j. Due to noise, xj prime does not coincide with xj. The transfer error is the distance between the points xj and xj prime. On the other side, the Sampson error models the distance between xi hat, xj hat on image I and j respectively. Here, xi hat, xj hat is the maximal likely estimation for the feature's true locations. This way, the Sampson error could better model the feature's measurement error and improve the DVIO's pose estimation accuracy. So here, the core idea is to replace the transfer error by Sampson error for the far range feature and the near range features. For the near range feature, the Sampson error is defined by this equation here. The epsilon and the Jacobian matrix J are defined by these equations. The detailed derivation of these equations can be found in the paper. For the far range features, the Sampson error is computed according to this equation as well. We run some experiments to test their pose estimation accuracy. We select the Wins model as a benchmark to evaluate their performance. 8 datasets were collected by holding the Robocane and walking along a 20-meter straight line at a speed of 0.7 meters per second. We use the endpoint error norm to evaluate the accuracy. The results are tabulated in this table, from which we can see that DVIO achieved a better pose estimation accuracy than Wins model, and the use of the Sampson error improved both the accuracy and precision of DVIO. Next, we tested the visual positioning system by working with the Robocane in a number of looped trajectories in the engineering east building of our university. The results demonstrated that the visual positioning system functioned very well in locating itself in the 2D floor plan. The finger shows the Robocane's trajectory about 200 meters, estimated by the visual positioning system for one of the experiments. We also recruited 5 sighted human subjects outside our lab, and they are blindfolded to test the Robocane in 3 different navigation tasks. The results are tabulated in these tables. It shows that with the assistance of the Robocane, the successful rate of arriving at the destination is greatly increased compared to cases with the white cane. Also, the number of hitting obstacles using the Robocane is much smaller than that with the white cane for all 3 tasks. The results demonstrate that the Robocane is effective in assistive navigation in an indoor environment. To conclusion, we present a new visual positioning system for an RNA to assist the visually impaired with wayfinding and obstacle